I have the matrix B, 1, 2, 3, 6. I want to take the single value decomposition of it. So use sigma V transpose, where U and V are orthonormal, and sigma contains the single values. Yes. So again, I will first calculate B transpose B or B transpose. So in this case, it doesn't really make any difference because I mean we have a 2 by 2 matrix, so that we take B transpose B or B transpose. We will in both cases again get 2 by 2 matrix. Yes. Yes. So let's take B transpose B. So then we will find our matrix V. Okay, remember if we take B transpose B, we then can find our matrix V. And if you find B transpose, if you would find B transpose, you would then find our matrix U. Yes. So yes, we calculate our B transpose B, and then yes, I mean let's do it. I don't know. We get like what? We get like 1, 6, 2, 3. That's B transpose times 1, 3, 2, 6. And so if we do matrix multiplication, we get 10, I think. 18 plus 2, so 20. 20, 36, and 40. Okay, if I'm not wrong. Yes. So I hope it's correct. Yes, it seems correct. And so now I find the eigenvalues of that. So I take the determinant of B transpose B minus lambda I is equal to 0. So I is the identity matrix. And I will find, if you do that, you will find that your first eigenvalue, so lambda sub 1 is equal to 50. And your second eigenvalue, lambda sub 2 is equal to 0. Yes. So now I have those two eigenvalues, so I can find the eigenvectors V sub 1 and V sub 2 associated to it. Again, V sub 1 and V sub 2 because we took B transpose B. If we would do B times B transpose, we would get the same eigenvalues, but then you would find U sub 1 and U sub 2. Okay. So yeah, you can also do it in the other ways. It really doesn't matter in this case. And it's not quicker or whatever if you do it in another case. Yes, if you do it with B transpose first. It's like just like in some cases, like if you don't have a square matrix at the beginning, in some cases if you do B transpose B, you will get, like for example, get the 3 by 3 matrix, but if you do B transpose, you will get the 2 by 2 matrix, and so it's quicker to deal with the 2 by 2 matrix first. But yes, here it doesn't matter. Yeah, anyway. So if yeah, we get our eigenvectors. V sub 1 is equal to 1 over square root of 5 times the vector 1, 2, and V sub 2 is equal to 1 over square root of 5 times the vector minus 2, 1. And so yes, this is normalized because yes, we divide by the norm. So the norm of this vector is square root of 1 squared plus 2 squared, so square root of 5, so we divide by square root of 5, and the same thing here, square root of minus 2 squared plus 1 squared, so square root of 5. Yes. Yes, and so our matrix V is 1 over square root of 5 times 1, 2, minus 2, 1. Okay, so this is V sub 1 and this is V sub 2. Yes, V sub 1, V sub 2. Yes. Yes, now we can use the formulas again. That's yeah, U sub I. Here we need to write U sub I prime. You will see it in a minute. Why? U sub I prime is equal to 1 over sigma I times A. I mean here we have B. This is a B times V sub I. Okay, and I mean if you do it in the opposite way, you would have V sub I prime is equal to 1 over sigma times I times B transpose. I mean A transpose B transpose. I mean yeah, B transpose here times U sub I. Yes, but here you need the first formula, not the second one. Yes. So yeah, so in this case, I mean, if you do that, sigma sub 1 is the square root of the first eigenvalue, so the square root of 50. Yes, so we have 1 over square root of 50 times our matrix B times V sub 1. So where is V sub 1? It's here. So you would have like yeah, we would have 1 over square root of 5 times 1 over square root of 50 times, yeah, 1, 3, 2, 6, 1, 2. So that will give me like 5. Yes, so like vector 5, 5 and 12 plus 3, so 15. Yeah, so that's what's written here. Yes, and yes, so is this normalized? I don't know. Maybe it is. Is this normalized or not? I don't know. Anyway, but what you can see here is we have the vector 5, 15, and I mean that's just 5 times the vector 1, 3. Okay, if you multiply the vector 1, 3 by 5, you get 5, 15. Okay, so you can as well take the vector 1, 3, which will be simpler. So let's take the vector 1, 3. Okay, so I mean just what I did here is we have the vector 5, 15, and that's 5 times the vector 1, 3. So we can as well take the vector 1, 3. It won't change anything. And so if we take the norm of this vector 1, 3, it's simply the square root of 3 squared plus 1 squared, so the square root of 10. So that's why I wrote prime here. It's because, I mean, when we can make it simpler, we can simply take this vector u sub 1 is equal to 1 over square root of 10 times the vector 1, 3. Okay? Because 1, 3 times 5 is 5, the vector 5, 15. Yes. So I don't know if this is already the norm of this vector. I mean, don't know how much is 15 squared. Maybe it is. I don't know. I mean, 15 squared is like what? It's 150 plus is 225, I think, if I am correct. Plus 5 squared, so it will give me 250. Now I take the square root. So yeah, in fact, yeah, okay, this is already normalized. You can as well take this vector here. It's just that, I mean, it's the same thing as taking this vector here. Just that this is this times 5 is this one. Yes. I mean, yeah, of course, you need not simply times 5, but then you need to normalize it. Yes, but still, I mean, yeah. You can take this vector here or this vector here. Just I take this vector here because it's a smaller vector. Yes. Yes. And so sigma sub 2 is 0, so we cannot use the formula because we would divide by 0. And so we just need a vector. Remember, we just need a vector that is orthogonal to the first vector here, u, that we found, and then we need to normalize it. So here we are in 2 dimensions, so we can remember that if we have the vector AB in 2 dimensions, a vector orthogonal to it is simply minus BA, or B minus A would also do it. Yes. So we simply take a vector here, 1, 3, we switch both components, we get 3, 1, and then you put in a minus sign in front of the B or the A. So here I choose B, so we get u sub 2 is minus 3, 1, and divided by the square root of 10. Okay, the norm is still the same. Okay, so I mean it's the square root of minus 3 squared plus 1 squared, so the square root of 10. Yes. Yes, so this is my u sub 2. Yes, and yes, also remember I said as we did, sigma sub 1 is the square root of lambda sub 1, so square root of 50. Sigma sub 2 is the square root of lambda sub 2, so 0. Yes. Anyway, and so our sigma matrix is has the same size, the same number of dimensions as our original matrix. So here we have a 2 by 2 matrix, so our sigma will be a 2 by 2 matrix. So we will put sigma sub 1 here and sigma sub 2 here. And remember the biggest single value first, so square root of 50 is first, and then the lowest single value as second element here. Okay, yes. So 0 here. Yes. Biggest first, and then the second biggest until you reach the end where the smallest one will be. Yes. Yes. So now I have my matrix sigma. I have my vector u sub 1 and u sub 2. So I have my matrix U, which will simply be the vectors u sub 1, u sub 2, my matrix sigma set, and my matrix V, which is filled with the vectors v sub 1 and v sub 2. So I will have v sub 1, v sub 2, and I take the transpose. Yes. So I have again my singular value decomposition. Okay. So this is U sigma, and this is V transpose. Yes, so V has the vectors v sub 1, v sub 2, U has the vectors u sub 1 and u sub 2, and sigma has the singular values in diagonal, sigma sub 1, sigma sub 2, and 0 elsewhere, and the biggest single value first, and then the second biggest, and so on. Here we have only 2, so we have the biggest first, so square root of 15, and then square root of 0, so 0. Yes. Yes, and so this is our single value decomposition. Yes, so yeah, what we did, we found the eigenvalues of B transpose B or B transpose, and then we found the eigenvectors V sub 1, V sub 2, or U sub 1, U sub 2, depending on if we found B transpose B or B transpose. Here we found B transpose B, so we will find the eigenvectors V sub 1, V sub 2. Yes, then the single values are simply the square root of the eigenvalues. We can find the remaining vectors that we need. So here we found V sub 1, V sub 2, so we will find U sub 1, U sub 2. Here we had 0 as a second value, so we just needed to find a vector that is orthogonal to the first one and then normalize it. That's what we did. Because you are in 2 dimensions, you are lucky. Again, you can use, if you are in n dimensions, you can maybe use Gram-Schmidt or something else, I don't know. But yes, in 3 dimensions, you can use the cross product, and in 2 dimensions, you can, just do this little trick. You switch both coordinates, and you put a 1 in front of one of both coordinates, and then you have the orthogonal vector. I mean, the vector that is orthogonal to the original vector. Yes. And yes, that's what we did. So we have our single value decomposition. Remember that U and V are also normal, so they contain vectors that are of length 1 and that are orthogonal to each other. If B is an m by n matrix, so m is the number of rows and n the number of columns, U will be a m by n matrix, and V a n by n matrix. Yes, just to remember. But because here we have a square matrix, I mean m is equal to n, because we have a 2 by 2 matrix, I mean U and V will have the same size, the same number of dimensions. Yes, they will both be a 2 by 2 matrix. Yes. Yes, so I hope that's it. I hope you understood it. And yeah, I mean, the geometrical representation of what we did is we have some basis V, a vector x in this basis V, and then vector x expressed in this basis V, and then we applied then B to it, and that's like B does 2 things. It rotates and stretches. So it's like saying we have a rotated basis U, and we stretch it of the basis of this matrix U. I mean, each of this basis vector U, we stretch it by some amount each, and that will do the same result as applying B to our vector x in this V basis. And so that's from where we get this. I mean, of course, there's a vector x here. Sorry. Because we apply to a vector, yes. Bx is equal to U sigma V transpose. I mean, the sigma here is in front, but remember that sigma contains singular values, and those are simply scalars for each vector V sub I, and so you can put it in front or after, it doesn't matter, okay? So these are scalars, so it means that you put the scalar A times some vector blah blah blah. It's the same thing as vector blah 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 times A. Yes, I hope you see what I mean. So yes, so that's what we did. Basically, we we had some random vector, we applied this transformation to it, and we just claimed that it's the same thing as that we have another basis U, and we applied the single values to it, and that's the same thing as if you had our original vector in the basis V, and then we apply B to it. That's the geometrical meaning of what we did. If you can not draw it with your vectors and you have your other bases, you would maybe get something like that. I don't know. Then it's like saying that instead of taking that and rotating with B and then getting a result, you take this other basis and you stretch each of these bases vector by some amount to get the same result. That's what we did. Yes. So I hope you get some geometrical intuition of what we did. I hope it was clear. Thanks for watching.